here for the rest of the lecture then. Okay, so this first part, I'm going to start section 6.1, give you something to do. You'll be bored. 6.1 actually is really easy. It's a review of exponentials and logarithms. If we get time, I might do the derivative of the logarithm. Probably we'll do that next time. The idea is that we've got all these neat derivatives. We know what the derivative of sine and cosine is and all these things. But what is the derivative of a logarithm? Well, that's what's coming up, or the derivative of an exponential function. We want to be able to do those, right? So review of exponentials and logarithms first, and then we'll deal with their derivatives using those properties. Part of the reason we have to do this is people tend almost uniformly to forget a lot of logarithm properties when they come up with algebra, right? So just to make sure that we're up to speed on all those. There are different ways of introducing these. This is one of the frustrating things. Some books actually introduce the logarithm in terms of an integral and then redefine it using calculus, which is kind of a neat way to do it. Other books define it the traditional way from algebra, and then you have calculus limits that you have to take. So this version of the book does that, although the other versions of the same book do it the other way for people who want it the other way. We're going to let E be the special number, which will be the limit as x goes to infinity of 1 plus 1 over x to the x. Okay? So we'll define that in terms of calculus. And if you calculate that limit by running your calculator a long time and seeing what the big numbers here and seeing what you're getting, what you find out that this is equal to is 2.71828, and goes on forever with like pi without a repeating pattern. So that'll be E. And it turns out to be a very special number in a lot of ways. I like this example just for fun. Seen compound interest before? Remember the compound interest formula, anybody in business? In the theory of interest, we have this equation for compound interest, that the amount you invest, A, or the amount you have in your account, A, is the principal, the amount you invest, times 1 plus the interest rate you have over N, the number of periods per period, the number of periods per year, to the NT. All right? So here, A equals the value of the account or your total amount. P is the principal, the amount to invest. R is the annual interest rate that's quoted. But it's also compounded N times per year. So N is the number of compounding periods. Like if it's compounded every month, it's 12. Compound periods per year. I don't make a run-on sentence. We're off the edge here. Almost already off. Now I think I'm just off on the screen here. And T is the number of years. Let's see, can I see that barely? T equals the number of years. This equation is kind of neat. I'm not giving this now for homework, but if you were to put at R equals 100% interest, suppose it's mafia rates, right? Charge 100%. And R is supposed to be in decimal form, so 100% is 1.001 is R. And suppose you invest $1, so everything's equal to 1 that you can make 1. You invest $1 at 100% interest, R equals 1. For 1 year. What do you get? You get your amount is 1 times 1 plus 1 over n to the n times 1, right? You get this formula. That's your amount of money after 1 year. You might say, well, I want to compound 12 times a year, then I get 1 plus 1/12 to the 12, right? I want to compound 1,000,000 times a year, 1 plus 1 over 1,000,000 to the million. What happens if I compound infinitely often? They call that continuous compounding, right? Continuous compounding. Then you get infinite interest, right? Because you let the number of periods go to infinity. Just taking the interest you get per period is the annual rate divided by n. So if it's 6% rate and it's compounded once per year, it's R is 0.06 and n is 1. Compounded 12 times per year, you got 0.06 divided by 12 is right, 0.05. Right? So that's the way this works. But continuous compounding lets n, the number of compounds periods per year, go to infinity to get what? An amount A equals limit n goes to infinity of 1 plus 1 over n to the n, 100% interest, $1 for 1 year gives you this, which is what? Yeah, it's E. That's the definition of E. If you invest at 100% $1 for 1 year continuous compounding, you'll get E dollars back. And in fact, more generally, if you use this formula, if you call that star, also let n go to infinity and star, leaving T and P arbitrary. So you can invest whatever you want P and you can get whatever interest rate you want R. You can get similarly, I won't do it, but the amount is P e to the RT. So just let n go to infinity here, leave R and P alone, and you get PERT. That's the continuous compounding formula. And what you find out is if you have 100% interest compounded once per year, you get $1 on what, at the end of 1 year with $1, you have $2, right? You double your money at 100%. But if you compound twice per year, then you've got $1.50 at 6 months because you get 50%. At 100% interest rate compounded twice, you get 50% at 6 months. Then you get 50% of that again, which is 75 cents, and you got $2.25 at the end of the year. And if you compound 3 times, then you got $1.33 something and a third at 4 months, and then at 8 months you compound that, and a year you compound that with 33.333% interest each time. And you think, well, if I just compound an infinite number of times, I'll get an infinite number of dollars. No, you don't. You get E dollars in this limit. In other words, you get 171.8% interest out of this formula, right? Because you got 2.718 times your original amount. Anyway, that's one place in which it comes up is the theory of interest. It's a nice formula. See it's all online, I guess, yeah. For compounding with n periods per year, if you let n go to infinity, you get PERT, the continuous compounding formula. So E is kind of an important number. Lots of applications. Comes up like that. With that motivation, what I really want to do, though, is this. Now, what if I want to find the inverse of that? Inverse of y equals e to the x. What is that? Yeah, it's log. Here's what I want to remind you of from algebra. This is unfortunately an algebra lecture. I'm up to doing calculus with these functions. Here's y equals e to the x, right? If I go over to 1, this would be 2.718 approximately. Right? Put in 1, you get y is e to the 1. If I put in 0, e to the 0 is 1, so it's any number of 0 except 0 to the 0 is not defined, and so forth. If we put -1, this is the number 1 over e. Right? And so on. That's what that looks like when you take e to the x. Just plugging in some different numbers, you can find some points on it. Now the inverse function, what should that look like? Remember from algebra that the inverse of any function is gotten by interchanging x and y and then solving for y. So if we draw the function over here, that's exact shape of this one, but it's flipped over the line y equals x so that we interchange the axes, then I get this kind of a graph. It's the same shape flipped over this line y equals x. Flip this here properly. And this is x equals e to the y, then I just interchange the coordinates. But look how it passes the vertical line test, so it also makes y a function of x to do that. What should we call this function name? Y is a function of x. We'll say it's also known as, aka, y equals ln of x, because it makes y a function of x. It passes the vertical line test. And because this was a asymptote, but the x-axis was a horizontal asymptote of e to the x, when you flip it and interchange the axes, that makes the y-axis heading towards minus y an asymptote of y equals ln of x. So we define y equals ln of x to be the function that is the inverse function of y equals e to the x. Which we know it does have an inverse. Remember what it has to be, what you have to have have an inverse function. If no vertical line intersects a curve more than once, then it's a function. How do you know if it has an inverse? This is the tricky algebra here. If no horizontal line intersects a function like this one, because e to the x is always increasing, no horizontal line intersects more than once. Then when I flip it, these horizontal lines become vertical, no vertical line will intersect more than once. There's the proof. Because we can prove the derivative is positive, so this is increasing. No horizontal line intersects more than once. When we flip it, no vertical line intersects more than once. That proves that the inverse is a function. Consequently, we'll call it the natural logarithm. And now you have this kind of property, right? If you have any point A, B on the e to the x function, then there's a sister point over here, B, A, because after all, that's how we got it, right? We interchanged x and y in the two equations. X equals e to the y instead of y equals e to the x. And now you notice from this point, from this thing, that if I take natural log of e to the a for any number a, well, e to the a is b. This is ln of b. But this is the ln of b function. I have to get back a by this thing. Right? And so ln and e undo each other. That's the property of inverse functions. Also, the other way, e to the ln of b is a. The e to the a is b, right? So e and ln undo each other. That is, if you write x and y instead of x instead of a and b, by this definition, e to the natural log of x is equal to x. They undo each other. And if you take natural log of e to the x, you get x back. They undo each other. They're inverse functions. However, you do notice one thing. This is wherever they're defined. Where is logarithm defined? Where is ln x defined? Only for x positive, right? Because this was an asymptote here, it never touched the x-axis. The y is an asymptote here, it never reaches the y-axis. It's only defined for x greater than 0. ln of x defined only for x positive. Oh, where it's defined, these properties hold. Right? So there's some things about their graphs and their properties. So this is a useful formula. Now the book gives it two other ways too. You can also let x go to 0 from the right, or let this be 1 plus x to the 1 over x, for instance. So give some alternate definitions in there. I like this one the best because it looks like compound interest. Okay, I don't want to do all the proofs of these things. I've got to get on to the review here, but if I take e to the ln of a times c, actually, let's do it the other way. Oh, let's just do it that way. E to the ln of a times c. By our inverse property, this is equal to ac, right? By the inverse property we just wrote. And now a is equal to e the natural log a, and c is equal to e to the natural log c. And now exponents add on exponentials from our properties before. So this is e to the ln a plus ln c. What have I established from that?
You can add.
Yeah, I just established a property of a logarithm. This holds for any exponent, and there's only e to a number, it only gives one number, right? It's an increasing function. So if you take e to a number and you get a number, then e to something else with the same number, these two numbers have to be equal in order for e to them to be the same, right? It's an increasing function. So these two numbers must be the same. ln ac must be equal to ln a plus ln c is a property of logarithms. Logarithm of the product is the sum of the logarithms. There's the proof. Using your properties from exponentials. Similar proofs that we don't want to ask you on the test, but I just wanted you to see that all this works. Similarly, if you take natural log of a divided by c, to a completely analogous proof, actually, you get ln a minus ln c. That's another one, which means it's a special case if you put a equals 1 in this one, we get another useful property. That ln 1 over c equals 1 is equal to ln 1 minus ln c. And now there's another thing I want you to see over this graph over here. Back to this one just for a minute. On this original definition, right? Here's e to the x. We know e to the 0 is 1, right? So this is the point 0, 1. On y equals e to x. When I take the inverse, I interchange x and y coordinates. So this must be the point 1, 0 on the logarithm. 1, 0 is a point on the logarithm. And also this point here that I took 1e corresponds to a point over here, e1. What does that tell you? Another property of the logarithm I haven't written down yet. This one tells you, since it's the logarithm function, that the logarithm of 1 is 0. ln of 1. So this point here implies that the logarithm of 1 is 0. And this one here, if you take logarithm of e, you have to get 1. And it's just because the point 1e becomes the point e1 on the inverse function. So by defining the natural logarithm to be the inverse of the exponential, natural log of 1 is 0 and the natural log of e is 1. Those are to be memorized. Want to memorize these? You want to memorize these? I'll store all these things you need to remember. Now we just want to recall all these properties because they're going to come up a lot now. Log of 1 is 0, log of e is 1. I think you remember e to the 0 is 1 and that kind of thing. E and ln are inverse functions, so this holds. You picture it, you can pull it off the graph, there's the proof. Because AB is on this function, BA has to be on this one and so forth. And we have these properties, and then we go over the other side of the board. know? And we find out also these three properties that you want to memorize also. The logarithm of the product is the sum of the logarithms. Logarithm of the quotient is the difference in the logarithms. Logarithm of 1 over c is a special case of this. Oh, wait a minute, ln1 is 0. Huh? So ln of 1 over c is actually just minus ln c. Logarithm of 1 over a number is minus the logarithm of the number. So those are useful properties to do. Also with a similar proof to this, and I don't want to spend too much time doing algebra, but natural log of, the book writes it this way, a to the r is r natural log a. This is a very important property. It pulls the r down. So you want to memorize all those formulas. They should be familiar from algebra anyway, but we sort of rework them in a sense. Yeah, actually, yeah. Similarly, without going into all the details, because you can spend a week on this easily redoing algebra class. If we take log base b of x, how shall we define that? We're going to say yeah, it's the inverse of b to the x in general. So y equals log base b of x will be inverse of y equals b to the x. Gives analogous properties. If you work them out the same way, you get log base b of 1, as you said, is equal to 0. Log base b of b is equal to 1. Those are analogous to these two properties right here. This one here really is log base e is what it is. Inverse of e to the x. So we can also call it log base e of x, right? By this definition. But we like this shorter notation. It's more convenient to write 2 letters than 4 over here. It's the LOGE, right? A little easier. Log natural, yeah. What we do is we'll use this special notation, but it's also just a logarithm base e by this day. Let me just write that down. Log base e x is the same definition as ln. And we get analogous properties with analogous proofs. So we'll lead to that log base b of any product AC is similarly log A plus log C. These are a lot to memorize. This is why nobody remembers them from algebra. I hope I'm not putting you all to sleep with this. If it's too boring, then I can skip over this and do the calculus right away. But I think most people don't remember this all that well. So just try and review. Log base b of A over C, just like that one. And it's analogous to proof to what we did for the product there. Is log A minus log C. And log is a special case of that. So put A equal 1. Log of 1 over C is minus log of C. In any base. And then maybe you remember this property. This is just notation. Just like we put ln of x as special base, that's log base e, right? The real important number that we get with infinite. We can say, well, log base 10 comes up a lot. You know why log base 10 comes up a lot? Real good for powers of 10. Like if you have $1 million, what's the log? Well, we'll write it. I need to write this last property here. Anyway, let's write log of a to log base b of a to the r is also r log base b of a is the other property right there. So, and now I'll introduce this notation. just like log base e is important, log base 10 is important. We'll let log of x, if you write that and there is no base, actually there is a base, that means the common logarithm. It means log base 10, so I'll put DEF, that's the definition, it means log base 10 of x. There is always a base, you just have to, if you leave it, it's like when you put no number here, what does it mean? It means it must be square root, right? If you put a number here, that like the 3 here, that's cube root, but if you leave it off, 2 is assumed. Similarly here, if you leave 10 off, 10 is assumed, right? It's a common logarithm. And it has these neat properties for finance and so forth. Right, we says it pulls down the exponent. Log of a to the r is r log a. If I take log of, let's say, $1 million, log of 10 to the 6, what's that? Yeah, well, you're ahead of me, good. So you remember it. You pull the exponent down. Log of a to the r is r log a. But what is log base 10 of 10? Right? Log with the 10 omitted, 10 is assumed. Or without base omitted, 10 is assumed. But log base 10 of 10 is 1, right? This holds for any base. So this is 6 times 1 is 6. And so if you get log of 10 to any power using the common logarithm, you just get the power out of it. So that's kind of nice. If your logarithm of your dollars is 6, then you got 10 to the $6, right? That kind of thing. So logarithm is really useful just because we save numbers in base 10. If you take a log base 10 of something in science and it's 327 million, right? Well, that means that logarithm of it is between 6 and 7, right? Logarithm of 10 to the 6, or $1 million would be, I'm sorry, it's between 8 and 9. Logarithm of $100 million would be 8. 100 million is 10 to the 8th. Log of a billion will be 10 to the 9th. Log of 10 to the 9th, a billion will be 9. So you got a number between 8 and 9 as the logarithm. So if you take the logarithm of a number and you get a number between 8 and 9, then the original number was between 10 to the 8th and 10 to the 9th. All right, so there's a useful notation that we won't use much, but logarithms aren't complete without introducing that. Sometimes in computing science, you'll see LGX. What does that mean? This means log base 2 of x. Occasionally in textbook, it's not used all that much, but you might see that one somewhere. We won't use it in here, but I'll just make that additional note. You might see that. And you have to be careful because in computer programming, if you say log x, it can mean natural log, depending on and if you want the log base 10, you write log 10 of x. So programming has its own specifications. You have to be careful. Log doesn't mean log base 10 in some programming languages. It means log base e. They don't put ln of x in programming. They put log for ln. So there's those kind of changes in notation. It's very frustrating from time to time. We'll just stick to log without the base is log base 10. ln is log base e, and otherwise you put the base, right?
And you change bases.
Yeah, so let's go ahead and do that one. I thought to do that one anyway. There's a change of base formula that's very useful to us. That's often forgotten in algebra because you don't use it very much. Change of base formula. If you have a logarithm in one base, this is useful in computer science if anybody's interested in that. I think you are. Log base b of x is equal to log base a of x over log base a of b. For any allowed base a, you're only allowed to put the base positive and not equal to 1, by the way. I didn't write that down here, but logarithms aren't defined otherwise. Like if I try and invert the function y equals 1 to the x, it's a horizontal line. It doesn't have an inverse, right? If I try to make an inverse, it would be a vertical line, and that's not a function. So there is no log base 1 because it would be a vertical line. It's not a function. And if you don't have logarithms for base less than 0 because you get roots and negatives and so forth. And you can do that complex variables in class, but we'll assume bases are positive and not equal to 1. Maybe we should write that note. Log base b of x is defined only for bases b greater than 0 and not equal to 1. And then as we showed from the graph, the argument has to be positive. The other graphs are also that way. For instance, if I put y equals 2 to the x, right? It looks like that. It goes through the point 0, 1 because 2 to the 0 is 1. Goes through the point 1, 2 because 2 to the 1 is 2, etc. And if you take its flip over the line y equals x to draw the same shape function over here, just with the axes interchanged, this is x equals 2 to the y. Also known, since it's a function passes the vertical line test, as y equals log base 2 of x. And it goes through 1, 0, showing, since this one goes through 0, 1, this goes through 1, 0, showing that the log base 2 of 1 of 0 of 1 is 0. This property here equals 2. And it has this point over here, 2, 1, log base 2 of 2 is 1. So I mean, log base 2 of 2 is 1. So that's, but if you put a general b to the x and log base b of x, that's how you derive those two properties again. But you can see from the graph, the point is these all have an asymptote here. And so it doesn't cross the asymptote, right? It's like that. Lord of the Rings, none shall pass. It doesn't ever pass there. Got that vertical asymptote. So logarithms are only defined for x positive, since they only approach that asymptote. There is one quirk in here. These are the graphs for b positive. For b greater than 1, if you put b less than 1, like 1/2 to the x, it looks like that. And then its inverse flips over the line y equals x and goes through this point. Right? Something like that, I guess. And so those look kind of screwy. Hardly anybody uses a base b between 0 and 1, but the logarithms look different like that and that if you put a base between 0 and 1, but they are defined. We won't use them really. All right, so that's all those, and then the calculus properties we need. Of course, I include. We want to be able to do some of the following tricks for the problems that we have to deal with in here. Here's some examples. What is the log base 2 of 16? How do I evaluate that exactly without my calculator? I know. Yeah, awesome. How?
You just multiply by 2 until you get 16. Count it up.
Okay. I'm gonna
2 to the 4th is 16.
Yeah, you're absolutely right. I'm gonna rewrite it like this. When you want to evaluate a logarithm by hand, exactly, you can only do it when the argument is the power of the base. So you rewrite the argument 16 as 2 to the 4th. Now you use the property that the exponent comes down, or the inverse property, right? Log base b of b to the x is x by the inverse property. So this is just 4, right? Log base b of b to the x, since they're inverse, this is x. Or you can pull the exponent down and say log base 2 of 2 is 1, either way. So I use that property. And so you can evaluate these exactly when the argument is a power of the base. Like, for instance, what is the log? It's one of the homework problems. Log base 9 of 3. How do I write that?
To the 1.
Yeah. There you go. Yeah, I have to write 3 as a power of 9. Well, it's the square root of 9, right? So I log base 9 of 9 to the 1/2. Oh, then log base 9 of 9 to the 1/2 is just 1/2. Again, because log base b of b to the x is x. So you can do something like that, or log base 2 of 1 over 1,024. Anybody know that one? Computer science. When you do computer science, 1,024 is a kilobyte, right? I mean, in most things, a kilo is 1,000, right? You go run a kilometer, it's 1,000 meters, or 400 to say kilometer. So you run a kilometer or a kilometer, it's 1,000 meters. But if you say kilobyte, it's the nearest power of 2, it's 2 to the 10th. Is 1,024 is a kilobyte. You got 24 extra bits in there. So this one you rewrite since you memorized 1,024 is 2 to the 10th maybe if you're computer science major. This is 1 over 2 to the 10th is also the log base 2 of 2 to the minus 10. 1 over 2 to the 10th is 2 to the minus 10. Log base 2 of 2 to a number is just that number. This one is minus 10. So I want you to remember those properties from logarithms. Be able to do those exactly by writing the argument as power of base. Generally, you can't do that. I just have to give you a special number, but and you can check that in your calculator. Your calculator will do that and figure it out for you too. But I want to make sure we pointed that out. Okay. Then you want to be able to simplify some of these things. Put this these right here, rewrite in terms of natural log A, natural log B, and natural log C. The expression ln of A squared square root of BC. How about that? How am I going to rewrite that in terms of ln A, ln B, and ln C? Here's what you want to do is use those properties, right? It's a logarithm of a product. Logarithm of a product is the sum of the logarithms, right? Actually, let's do this first even. Let's write this as ln of A squared, and right, square root of BC is B to the 1/2, C to the 1/2, right? This is square root of B, square root of C by your property of square roots, and then you can write the square root of the product as the product of square roots. And these assume that A, B, and C are all positive. So you get square roots and negative. Now what can I do? ln of the product is the sum of the logarithms. I wanted to point out that property extends if you have a product of 3 things. It's the sum of the 3 logarithms. You just apply that theorem twice and you prove this theorem. So logarithm of a product of 3 things is the sum of 3 logarithms. Then you remember you can pull a power down. So this is 2 ln A plus a half ln B plus a half ln C. Those aren't really familiar, I hope. But there it is in terms of ln A, ln B, and ln C. Use these properties that you got for logarithms. I didn't tell you this was my 1 semester and 1 hour algebra course, did I? That's what we're about here. All right. Some of those courses online sound about like that. They're too good to be true anymore, I think. All right. So now we got the biggies here right at the end. Then we want to be able to solve equations using exponential. And there's a couple of them in here. Example. Suppose I want to solve an equation like this. 2 e to the 3x equals 7. This is what we often need logarithms for. How do you solve that? This comes up in finance because you're if you use PERT, A e to the RT, x instead of t. And you want to figure out, well, I know my interest is 7, but how many years did it take me to get there, right? If this is PERT equals $7, how many years X did it take me to get $7 if I put in $2 at 300% interest here, compounded continuously? Boy, I don't know. I have to be able to solve this equation. So remember how to solve these. If X is in an exponent, you use logarithms. How do I use logarithms to solve that? Yeah, log both sides. I can do it right now, but I prefer to divide by 2 first. So I'm going to say 1, isolate the exponential with x in it. You're right, though. You could take log down if you wanted. isolate the exponential. That means I'll divide by 2. And I'll write e to the 3x equals 7/2. Once that's all by itself, the exponential with x up at the top, I'll take the logarithm of both sides with the same base. Take log, same base as the exponential, to get rid of it, because right, they're inverse functions. I'll take ln, log base e, since my exponential is base e. And I'll take it on both sides, they're equal, their logarithms are equal. So this is also a true statement. And now comes the trick, right? Log base e of e to anything, it's inverses function. This is 3x, right? Log base b of b to the x, b to the p or whatever is p. So this is by ln of e to the x equals x. It's just the argument is 3x this time. All right, and then it equals ln of 7/2. I could write this as ln 7 minus ln 2, but I'm not sure that would be easier to do on my calculator, so I'll just leave it like that. And then I divide by 3. So what happens when we take the logarithm of both sides, x comes out of the exponent and you can solve for it. Now I've got x is 1/3 natural log 7/2 exactly. Right? That is the exact answer in terms of logarithms. So I just wanted to point out, you can do some homework with that. When x is in an exponent, you isolate the exponential, take the logarithm of both sides. Then it's just a simple arithmetic kind of problem here. Not anything hard anymore. So 3 is solved by other. So like arithmetic or something. What's left? All right. Multiply, divide, add, and subtract. And then finally, what if x is in a logarithm? Here's an example of a logarithm problem on the homework set. Suppose I wanted to solve this equation when x is in a logarithm, ln of 1/x plus ln of 2x cubed equals ln 3. How about that? And the strategy here is if x is in a logarithm, you can combine the logarithms. Combine logarithms using by your properties that you had. And then take the exponential of both sides with the same base. So let's combine the logarithms. Ln plus ln is ln of the product, right? So this is ln of 1/x times 2x cubed equals ln 3. This one we can leave off if we want, or we can subtract it over, right? Ln, let's see, this is 2x squared minus ln 3 equals 0. So I cancel part of these out and then subtract this over. Now, difference of logarithms, I write as ln of 2x squared over 3. That, and so you combine the logarithms like that and then take the exponential. And that gets x out of the logarithm. So x is an exponent. You isolate the exponential, take the logarithm of both sides to get x out. X is in a logarithm. You combine the logarithms, take the exponential of both sides to get them do each other. Take exponential, same base is easiest. You can use any base you want, actually, it turns out, but the easiest one is the same. Take the exponential, same base. Because then they automatically invert each other, right? So I'll take e to the left equals e to the right. Good. Well, e to the 0 is 1. And these e and ln undo each other. So this is just 2x squared over 3. When you take the exponential both sides, it undoes the logarithm. And now you just solve by old method, solve by arithmetic. Maybe you got a power in here, it might be algebra, but solve by arithmetic, etc. Might have to do a root or something. All right, so I'll multiply by 3/2 and get x squared equals 3/2. And then take the square root, x equals plus or minus square root 3/2. You can leave it like this. I don't expect you to rationalize the denominator. It's not easier to write that way. I do want you to reduce things. Don't leave square root 4, put 2. But if it's not simpler, you can also write that as square root 6 over 2 by multiplying top and bottom by square root 2. I don't think that's easier. This is fine too. These are both fine, of course. So there's two answers to that one apparently. Is there really? You have to be a little careful on these. When you combine these logarithms, like right here, if these were both negative numbers, this was undefined. But the product of negative numbers is positive. This is defined. So when you combine these things, you can introduce new solutions. So the last thing you need to do here is check your answers. If you get a logarithm of a negative in the original, you have to throw it out. And minus square root 3 over 2 doesn't work, right? You get log of a negative. So there's actually only one answer on this one. Check for log of negative. All right, that's it. We didn't do much with the change of base formula. Maybe I'll mention that again next time. But we wrote it down at least. Let's see if there's more. I don't want to take any more time on this. What would you like to do for the few problems today? The word run? Okay. Work. Okay. Yeah. I can stay after class if you guys have some more questions, by the way. Or you can come to my office hour tomorrow at 11 down at the end of the hall in MCS 113. I'll also be online. You can meet me out right on the board in that room. You can meet me virtually. Come in that way. Yeah. Let's see, work. There's a spring work one here. Was there more than one? There's a pool. There's two work ones, I think. Okay, let's do 5 then with the pool. Work. Find the work to pump out of pool to the top edge. If it's a rectangular parallel pipe, that's a fancy word for a rectangular box like that. So length 40 feet, width 20 feet, and depth 8 feet. Build to the top. What you do is you break this up into pieces. Think of it's easiest usually to put the 0 position at the top of the pool where you're pumping it to, and call X downward. And then you can partition the X axis from 0 down to the depth here, 8 feet. And we'll partition into n subintervals. X0 will be 0 and Xn will be 8. And then X1, X2, X3, and so forth. What we can do is this and say that the force on, we'll break this up into little slabs. And if you take the K slab, its width is delta xk because it's the increment in x from xk minus 1 to xk. And then it's also 20 by 40 for its cross section, right? 20 by 40. And so the slab, if you pull it out, (20 by 40 by delta xk) is its volume. So the volume of the K slab is Vk equals length times width times height, 20 times 40 times delta xk. You find the volume. Then that tells you the weight of the water. So the Fk, the force on the K slab, is the volume times the mass density, the weight density. Right, if you have this volume times this many pounds per cubic foot, then that gives you the force or the weight. Don't use the mass density, right? Because mass is not force, weight is force. And the weight density of water will be 62.4 pounds per cubic foot. Well, I'll give that to you in the test if you need it. Oops. Per cubic foot. So we can say that this is actually 800 rho is 800 times delta xk is dk, and then rho is 62.4. And this gives you pounds, right? Because this is cubic feet, and this is pounds per cubic foot. And they cancel. So that there's pounds as a weight, it's a force. That's how many pounds each slab weighs with delta xk. Now, once you've got the force, you've got it. Say the work to lift the K slab, work to lift K slab will be the force of the K slab times the displacement. Work is force times displacement. And the displacement is wherever the slab is at some point xk star, you could say. Some point in the case, force times xk star, force times displacement. So this is a hard one, isn't it? And so now you got, let's see, 800 times 62, 800 times 62.4 times delta xk from the last part here. And I'm multiplying that by xk star. There's dots here for the multiplies. So there's the work to lift the K slab, right? Now the total work is the work to lift all slabs. W equals sum, A equals 1 to n slabs. So that partitions the interval into n subintervals of the work to lift the K slab. What's more, you can let n go to infinity to get the limiting result. And what we get then is the limit n goes to infinity. Sum k equals 1 to n of this 800 times 62.4. Some books put 62.5 for a rounded number because water density kind of depends on what you do to it sometimes. You get a little salt in it, it's a little heavier, for instance. But pure water, I think, is 62.4. Anyway, times xk star times delta xk. There is the exact work to pull it out, but this by definition is the definite integral. It's the integral over the partition 0 to 8. Right, this is by definition of the definite integral of this thing with delta x replaced by dx, and this notation will mean this, and xk star replaced by x. So it's 800 times 62.4 times x. I've had people before, instead of figuring all this out, they just memorize this formula. But you have to be able to do it over the shape of whatever it is too. So you have to know cross-sectional area. Anyway, there it is. If you just evaluate that integral, it's 800 times 62.4 times x squared over 2 when you integrate it. Evaluated at 8 and 0. Comes out to be, this is where I told you need your calculator on the test. It's 800 times 62.4 times 64 has is 32. That's a decimal point detour multiplies. So that's how many, what? In pounds and feet, and forces in units of distance, work is in units of force times displacement, so it's foot-pounds in the English units, right? Sometimes I put LBS, it just doesn't write that. Sometimes they put a period on here, it's very frustrating. Got all that on there, maybe it's off, I need to move this a little, sorry. On now, yeah, there we go. So whatever that comes out to in your calculator. There's a hard one, huh?
Yeah, it's easy to mess up.
One of the big points in here is this is sometimes things you have to do is break up a problem, partition it up. In advanced calculus, we do this a lot. We'll partition it up and get an integral and say, aha, now this is for a mathematical model of some sort. Okay, what else should we do? Is there another, if you want to see the word problem with the spring, it's easier. Is that good? Okay, let's try that one. 7. A spring is attached to a mass in a frictionless table, a 20 Newton force. So this is going to be in the metric system this time. A 20 Newton force holds a spring at 15 centimeters from equilibrium. This one actually is tricky because of the next units here. Exactly, yeah. Newtons is for force means feet, kilograms per second squared. Right? The way you can get that, if I don't do too much tonight, just for the people that are interested in the physical sciences. What is a force? In Newton's law, it's force equals mass times acceleration, right? So in the MKS system, they call it meters, kilograms, seconds. There's also the CGS seconds, centimeters, grams, and seconds. We'll do the MKS system usually. Mass is in kilograms. Acceleration, what's that? It's d squared x dt squared, right? It's second derivative. So it's x is in feet, and d squared x dt squared, it makes it per second squared, dt squared on the one. So this is feet per second squared acceleration. Kilograms feet per second squared, we call newtons. So let's explain that. So when we put that up there, that's using meters. Always late at night. One time I didn't tell you, I was grading the students' exam. It's just terrible how you get tired late at night. And I got so tired I started falling asleep, and all sorts of strange things happened. I wrote, no Mardi Gras this year. I looked at been to a Mardi Gras. I've never been near one. I don't know. I have no clue where that came from to this day. But anyway, strange things like that happen sometimes. So you got to check me. All right, so 15 centimeters from equilibrium. Let's, for convenience, put the equilibrium at x equals 0. That's what always is convenient in the spring. All right, x equals 0 meters. Because we want to match the meters, kilograms per second squared. So I'm on feet from the last problem. So. Yeah, you guys didn't catch me. You're pouring something on the test when you write feet. All right. So now that's the case. What does that tell me? The force by the spring is equal to the force you have to exert to stop the spring is the Hooke's law constant K times X. Some constant K, and you don't know what it is. You have to figure out this K called the Hooke's law constant. For a spring, this holds, an ideal spring. They aren't perfect, but they make springs to try and be close to it. If you don't stretch them too far, they behave force is roughly proportional to the distance you pull it out. Pull it twice as far as twice the force. Right? So what is K? We have to find out from this. That means 20 for the force is equal to K times the distance I pulled. If it's 15 centimeters, that's 0.1 meters, 0.15 meters. So I use the same units. Meter, so 15 centimeters equals 0.15 meters. It's a trick problem. Huh? All right, so now you can divide through K equals 20 over 0.15. Now we're in the MKS system, meters, kilograms, seconds. Let's see. So if I let's see, that's 4/3 times 1/100th, so that's, 0.0, no, I'm 4/3 times 100, so it's, I guess 400. So I thought it's 4/3 times 100, it's 400 thirds. All right, so there's K, is 400 thirds, and now if K is 400 thirds, I have work was for a variable force like a spring was defined to be integral f of x dx from A to B. If it moves from position A to B, subject to a force F, this is what it takes. This is what it takes. Now, the force of the spring is actually minus kx because it pushes it towards x equals 0. But we're finding how much work it takes to oppose the spring, so we put plus kx. So I said plus kx is the force I have to exert to meet the 20-pound force of the spring. So we're getting k equals that. That's what's going on. The spring makes a negative force towards the origin. I pull it out. And this is my work here, f of x, is kx with k equals 400 thirds x. So this is f of x equals kx. And I integrate it. I'm pulling it from, the question is, I never wrote it down. How much work is required to stretch it from 15 to 19 centimeters? To stretch from 15 centimeters to 19 centimeters. How much work is it? You integrate the force, kx, from 0.15 to 0.19 because we're still using meters. So we'll get 400 thirds x squared over 2, plug in 0.19, 0.15, and take the difference. And we'll say calculator. I'd probably count 1 point for the calculator. I want you to get to here is what I want to see. On the test, what I'm going to do is I'm going to give you some of these questions here, and I expect you to show the steps. Don't just write the final answer, because most of the points will be on the steps. Well, that's a good one too. All right.
Tricky.
Yeah.
Make sure you keep
Yeah. If anybody's a chemist, anybody a chemist? I took 1/4 of chemistry. That's all I ever took. But boy, the chemists, they put, this divided by this times this divided by this. They have strings and strings of units, and they keep very careful track and cancel them out, or they'll make a mistake and probably blow the room up or something. They have a lot of units to do that with. Yeah, that's hard, isn't it? Most of the sciences are hard. That's why you get good money when you get out. Math is a really good major too. I always say that you should have some sort of specialty in another area. For instance, I took a bunch of physics when I was a math major, and so I got out and I got a job in the aerospace industry out of Vandenberg Air Force Base for a number of years. I also worked at Edwards Air Force Base and other places here in Oklahoma City, the Mike Monroney Aeronautical Center. But I was able to get into those places because I also had taken some physics and knew how to do that. Lots of these engineering places, they'll say, a degree in engineering, ABET certified, or in a similar discipline, which includes mathematics if you took those extra courses. So if you become a math major, take some extra courses. Maybe you want to be a computer scientist, you take computer courses. If you want to be aerospace, you take physics. If you want to go into some sort of chemical engineering, want to work for one of the oil companies here, maybe you take chemical engineering courses. So it just depends on where you want to go. I'll just give a small piece of advice here. Any other things you want to look at out of here? Arc length, washers, volume of the solid by revolving a plane region, and it's method of cylinders. Have arbitrary. This is another hard one. Maybe we should do this one. Number 8. I'll see if I can do the hard ones. Maybe you can do the other ones at home or come see me tomorrow. Sorry.
Is it number?
Yeah.
That one was difficult to do.
Yeah, that's what I'm doing. Yeah. Okay, so here's the pyramid. Use the method of cross sections to find the volume of the pyramid. with with 1 by 1 base square base. Those look like those Egyptian pyramids. And then whose square at x equals -2. Oh, that's at -2, and whose cross sections are squares perpendicular to the x-axis up to the tip at x equals 2. So I'll interpret this and say if you go out the x-axis, it starts at -2, and where you've got a 1 by 1 square goes up. This is 1. This is 1, and it goes up like that. X equals +2. That's the volume of that pyramid. So it goes from x equals -2 to x equals 2. It doesn't say that this x-axis runs right down the middle. Maybe that messes it up. Actually, it turns out it doesn't matter. If you put it up sitting on top and make it go down, it's still the same volume. As long as that same cross section is the same length, it will come out the same volume, it turns out. You can tell it from the volume formula. So this one, because it's not a solid revolution, we can't do cylinders, washers, or discs. We only have one method left, right? Erase this. That's the method of cross sections, right? The volume is equal to the integral from A to B of the cross-sectional area, A of x dx. Now, that's the formula we use to derive the cylinders and washers, or the washers and discs from anyway. Now, what is this? It goes, took that off the edge too far. Hope that's good. Can't ever see quite as well on that thing. I've got this one just barely, so I guess it's all right. All right, so I want to go from x equals -2 to x equals 2, taking cross section here. Here's how you do the method of cross sections. Take an arbitrary point x along the x-axis and figure what is the typical cross-section area A of x there, and that's what goes in here. And then the limits are where the cross-sections start, where the cross-sections end. So this is the integral from -2 to 2 of A of x dx. I just have to find a formula for A of x. What is it?
Well, you can note that it starts at 1. Look at the triangle, it's changing linearly. So you just do the y equals mx plus b, where it intersects at b and it goes down to h width, right? So
Yeah.
that would be negative b over h for the m plus b for the b value. And then you square that, and then that's your area formula. Because it's changing linearly from 1 by 1 to
So work
0.
this whole thing out, huh? Yeah. So what I'm going to do is I'm going to say, here's a line going down the middle of the top here, and it starts from 1/2 unit up, so that this is 1 unit across. So it starts at y equals 1/2 on the y-axis, right? It goes through on the y-axis up here at -2. So it goes through this point and it goes through this. So one way to get the equation of the line is to take the 2 points. This point here is at x equals -2, y equals 1/2. So people online can see it. -2, 1/2 is the coordinates of that point. And then this point is 2, 0. It goes through those 2 points. We could use, for instance, the 2-point formula from algebra, right? Remember this one? This is not the only way. He did y equals mx plus b, which is a great way to do it too. I'll just say y minus y0 equals, you can either use the slope or the 2-point formula, y1 minus y0 over x1 minus x0 times x minus x0. So there's the 2-point formula. This is actually just the slope. If you replace that with m, then it's the point slope formula. And these are my 2 points. I could call this x0, y0. Call this x1 and y1, and I just plug them in, right? Y minus y0 is 1/2 equals y1 minus y0 is -1/2, 0 minus 1/2 over x1 minus x0, 2 minus a -2 times x minus x zero, x plus 2, x minus a negative 2. There's the equation of the line that we see right there. Why do I do that line? Sorry about that. Because that's also the half the width of the square, right? If you get that height here, that's what we have here. This is the half height of the square. So it looks like y equals y minus a half equals the slope, which is minus a half over 4, is minus an 8 times x plus 2. Y equals 1/2. Let's see, 1/2 minus a fourth is a 4. If I just group all this over here, add a half over here, and that subtracts a 4. So minus an 8 back. So if you group all those together just by algebra, you get that. That's the equation of the line. It's got slope minus 1/8. The other way you can do it is say it goes down half a unit over 4 units, so the slope is minus an 8. And write y equals mx plus b. It intersects at 1/4 because it's halfway between a half and 0 here. That'd be an easy way to do it too, right? Maybe you prefer this. I just do the 2 point to do it generally. All right, so there it is. But this is 1/2 of the unit, 1/2 the side length. Because it goes right from the middle of the square to the top at any point x. That's this one. 1/2 s is y. So the side length is twice that number, is 1/4, 1/2, just double it, 1/2 minus a quarter x. And the side length, the area at x is the side length squared, since it's a square, is 1/2 minus a quarter x squared. So that's what I'm going to put in here. This will be the integral. From -2 to 2 of 1/2 minus a fourth x squared dx. Just evaluate that integral. How do I evaluate that one? Yeah, you multiply it out, or you make a u substitution. U equals 1/2 minus a quarter x. They both work great. Let's multiply it out. Sure, integral from -2 to 2. My half times a half is a quarter, right? It was a spoil. Minus 2 of these, minus 2/8 x twice minus an 8 x will be minus a quarter x. Plus this one squared would be plus 1/4 x squared. So they're spoiling this, and I just have to be able to integrate that. Your calculator may have functions to do this. I do want you to write out the steps here, but check your answers on your calculator. A lot of the fancy ones will do this, right? If you bought the one I recommended, just put this in here, it'll do it. Practice that. It's a good thing to be able to do. In the long run, people are going to do that anyway. I told you Murphy's law. Murphy was an aerospace engineer. If the airplane crashes, somebody dies. So if anything can go wrong, it will go wrong. Has to be your policy, Murphy's law. Because there's too much on the line. So this integrates to 1/4 x minus integral here is 1/2, or 1/4 times 1/2 x squared plus 1/4 times x cubed over 3. Since I'm out of time, maybe I'll just leave it there and say evaluate it to plus and minus 2. And you're done. This one is going to cancel out because if you plug it into 2 and minus 2, it's going to subtract itself. So you can drop that out if you want to save yourself. Plug in 2 and minus 2 to these and take the difference. Or do all 3 and do some extra work and these will cancel anyway. Well, put equals calculator. All right. If you want, I'll stay a little late, but I guess we're done for tonight. So thank you for coming in. And best wishes. Hopefully those are most of the hard problems. Difficult, but that's just making sure we keep mistakes. Yeah.
Hey, Dr.
Let's
Stapleton.
see my flashcards. I have some flashcards that I made for this class.
Thank you, everybody, for coming in.